All right. So yeah, what we've discussed in the past mostly was kind of data manipulation and creating formulas in Excel. And those videos will be posted as well. Um, but today I'm going to focus in on um, once we've calculated all the data that we are interested in, and we've developed or we've kind of taken a look at it and wrapped our head around what sort of data we have. How can we go about creating some questions that we might want to test statistically? And how can we do that in Excel? So if you haven't done any hypothesis testing in Excel, that's what we're going to focus on today. All right, so let me pull up my PowerPoint here and I'll share my screen. All right, so I'm going to go through this kind of quickly, and then we're going to focus on the last couple of slides where we're going to bounce back and forth between this PowerPoint and analyzing that National Atmospheric Deposition Program data set that we downloaded last time. So yeah, we're going to be focusing in on how do we develop and then test hypotheses. And the caveat here is this is way less than you will get in a true statistics course. So those of you who have taken Stat 3850 already, you've probably gotten way more than I'm going to go over today. But for those of you who haven't done any of this, this is going to be kind of like a primer for your more in-depth stats discussions. And hopefully it'll teach you some things in Excel that you may not realize were options. All right, so we talked about this briefly when we were talking about the responsible conduct of research, but scientific process generally consists of a number of steps, and you can find different variations on this, but including observation, and then developing a question or hypothesis based on these observations. And then we got to come up with some way to test those hypotheses, analyze our results, come to a conclusion, and then refine and repeat those experiments. So the example that I gave you guys was a very simple one. So we make the observation that some trees drop their leaves in the fall. We might hypothesize, oh, the sunlight also decreases as we move into fall. So maybe that's what's causing that the leaves to fall. We design an experiment where we're going to take some trees and we're going to give them artificial sunlight throughout the fall and see if they don't drop their leaves. And then we're going to compare that treatment to our control group or a natural tree that's exposed to the natural sun cycle. And we're going to analyze those results. And then we're going to potentially repeat the experiment going forward. But the question that we're focusing on here is, how do we come up with these testable hypotheses? And then how do we go about testing them? How do we compare these results? When I say compare the treatment to the natural, can we just say, okay, this tree looks like it dropped fewer leaves than the other one? Or how do we go about actually testing those in a rigorous way? So there are a couple of steps here that are really important. One is developing a testable question or falsifiable hypothesis. So here's another example. We've got the observations. If you look at the images over here on the right, these leaves have these little brown pock marks on them. We call this stippling. And this is what happens when some plants are exposed to high ozone in the atmosphere. So large pollution events can have high ozone, and we've seen in the past that ozone exposure damages crop leaves. We've also seen that crop yield is affected by the temperature in which the crops are grown. So that's this bottom figure down here. If we keep the air temperature really low, we get lower growth. We raise the temperature up in a greenhouse, let's say, we get higher growth. We raise it up too high, we get decreased growth of this particular plant species. It seems to like it at about 84 degrees Fahrenheit. And we know that both ozone and temperature are predicted to change as our climate changes. So what are some questions that we might be able to develop based on this set of observations? Somebody help me out here. Let's come up with one that's focused on ozone. So in this bottom one, we grew plants at different temperatures. What might be a similar question or experiment we could do with ozone? All right, I'm just going to ask somebody then. One at the bottom of my list here. How about Sam? You have any guess on a question we could ask or an experiment we could do?
I guess something between I'm not really sure.
Okay. How about Jacob? Can you help us out?
I'd say that we could probably try growing them at different levels of ozone.
Sure. We could do the same thing, replace temperature with ozone here. Start some out at really low ozone, crank it up until we basically kill the plant. Yeah, so the question there would be, how much does plant growth decrease as ozone increases, or something along those lines? And the way that we phrase these questions as scientists has to be pretty precise. So there are kind of better ways to phrase some of our questions than other ways. So, I call this a good science question. What I really mean by a good science question is it something that we can test? And is it something that we can test through experimentation or modeling or rigorous statistical treatment? All right, so a testable hypothesis here. So what this means is that we have to have some sort of hypothesis that is falsifiable. And that term falsifiable just that means that we could, based on our experiment, we can disprove this hypothesis if we get certain results. All right, so I ran into this in a couple of people's papers, and you may already know this, but we never prove anything in science. Right, so if you're writing, this research proves my hypothesis that whatever, you generally do not see the word prove in scientific writing. And that's because, we can only assume that what we found is true until somebody comes along and disproves it. So these falsifiable hypotheses have to be stated in a way that we can do some sort of test to disprove them. The best hypotheses are also laser focused. So we've been going over this with your kind of quantifiable questions, and when we start to get too broad, it can be an issue. So we want to focus in on one particular question, and that means specifically defining our major variables in the question. All right, and there are two ways that we write hypotheses, essentially. The one that we kind of think of, the more common terms that we think in, are these alternative or active hypotheses. And I'm going to use this H sub A to denote the active hypothesis. And we contrast that with the null hypothesis. And I'm going to give that the symbol H sub 0 here, H null. All right, so an example of a active hypothesis here. This is one that I was working on for a while, teaching responsible conduct of research and yeah, this course used to be ENV 3105, will decrease student academic integrity violations. All right, so that's an active hypothesis. I'm saying some action that I'm going to take, some experiment that I'm going to run is going to cause some sort of effect. The action I'm taking here is teaching RCR. The effect is decreasing academic integrity violations. The null hypothesis, we write instead, some action will have no effect. So here, teaching RCR in GES 3105 will have no effect on the number of student academic integrity violations. So here, this is my null hypothesis. I'm saying my intervention is going to have no effect. And in reality, it's these null hypotheses that we test with statistics, like the ones we're going to go over today. All right, so here, going back to our example of ozone and temperature impacts on crop yield, I'll go through a couple examples of testable hypotheses. All right, and I'm saying this one, it's okay. And this is an active hypothesis. Increased ozone and temperature will decrease crop yield. It's okay, but there are a couple of things that we could do here to improve this, because really, we've got a couple things going on in there. So we could say, we could be more specific on what we mean by crop yield. So increased ozone and temperature will decrease the number of peas produced by snap pea plants. All right, so now we've given a specific plant type. We've given the variable that we're going to measure. We're going to count the number of peas produced by each plant. So we've gotten more specific here. But we still have this issue. We've got a couple other variables in this hypothesis. So it would really be better for us to break these out into multiple hypotheses. So in this first one, we've got increased ozone will decrease the number of peas produced by snap pea plants. So that's where we're going to do Jacob's experiment of increasing the ozone that we grow the plants at. The second one, increased temperature will increase the number of peas produced by snap pea plants. All right, so we know increased temperature, plants like higher temperatures to a certain extent, it's going to produce more peas. And then we might have another hypothesis, combined increases in temperature and ozone will decrease the number of peas produced by snap pea plants. So this would be where we run an experiment where we're altering simultaneously both temperature and ozone concentration that the plants are grown at. All right, and the reason that these are better is because now we can do a specific statistical test to falsify each one of these hypotheses. And we can kind of tease out the impact of each variable on our measurement of interest, the number of peas produced. Okay, so here's where we're going to get into the Excel work for today. And let's see, we've got, oops, sorry. We've got, oh, sorry, a couple other things here that I need to cover before we get into actually doing this in Excel. When we're testing these hypotheses, we're using specific statistical tests, like I said, and we're not trying to prove our active hypothesis, but we're trying to disprove our null hypothesis. And the power of our statistical tests the ability for these tests to actually discern differences between treatment groups or between variables is dependent on how we run our experiments. So there are a couple of things that we need to consider when we're designing experiments that can impact our ability to do useful statistics. So one thing, like I said in the example with the hypotheses, we want to isolate variables. So when we're talking about variables, we use two different terms here to describe different types of variables. Independent variables are those that are not dependent on other variables in our system. So these are the ones that we're going to experimentally manipulate. We're going to choose the values of these variables, basically, for our experiments. And then we're going to look at the response of the dependent variable based on our manipulation of the independent variable. So our dependent variable in the previous example would be the number of peas produced. And our independent variables would be ozone and temperature. So yeah, these dependent variables, these are our response variables, the things that we're really interested in measuring. When we're designing experiments, we also want to make sure that we've got proper control groups. So in the example of growing our plants at different ozone concentrations, our background ozone concentration in the atmosphere is about 20 parts per billion. So maybe that's our control group. We're going to grow plants at 20 parts per billion ozone. Then we're going to crank it up from there, and those will be our treatment groups. So it's something that we can compare back to see if our independent variable actually has an impact relative to normal conditions. And then we want to make sure that we are replicating our experiments. So what that means is that we have enough independent measurements to be able to get an idea of the distribution of the variables that we're trying to measure. And I'll give you an example of that in a minute here. So if we were to just grow one plant at higher ozone, that's great. But if we could grow 10 plants and get an idea of how consistent the effect is, that would be better. And then we want to make sure that we're using methods that give us accurate, precise values for the variables that we're measuring. Okay, so let's get into a little bit of what we can do with Excel with this atmospheric deposition data set. Actually, before I go on, are there any questions on anything I've talked about up to this point? Okay. So going forward here, if you guys don't have that data set open yet, go ahead and open it back up. And I'm going to walk through it on my computer here so you guys can see what I'm doing. And if you're able to follow along, I realize this is kind of hard if you're, if you have only one monitor, but you can always go back and watch the video and try and walk through it at the same time I'm going through it on the video. So depending on the question that we're asking, that's going to determine which statistical tests we want to use. So we want to find the statistical test that is appropriate to our specific hypothesis. All right, so if we're interested in whether or not two variables are related, we're interested in whether or not, let's say, increased carbon dioxide concentration causes a decrease in ocean pH, so ocean acidification. And we want to know whether those two variables, atmospheric carbon dioxide concentration and ocean pH, are related. We would run a correlation, or we'd make a correlation plot. And then the statistical test that we're going to do is a linear regression. Yes, there are other different types of regressions out there that are not linear. The one that I'm going to go over today is a linear regression. So the example I have over here on the right is from our atmospheric deposition data set. If I wanted to know whether or not the concentrations of ammonium and nitrate are related, the first thing I might do is create a scatter plot like this. So I'm plotting the ammonium concentration on the x-axis and the nitrate concentration on the y-axis. And we can kind of see here, I've put this line of best fit in here, a linear trend line. And I've got my equation for the line and the r² for it up here. And this r², 0.628, that's pretty high for environmental data. So I might be tempted to leave it at that and just say, yeah, that's pretty high r². I don't see that r² all that often in nature. So these two guys must be related. But we haven't really performed any statistical tests here. And you know, there's considerable scatter in this relationship. So I might not be able to say just from looking at this very reliably that these two variables are related. So what I'm going to do instead is run a linear regression. I'm going to show you how we do that in Excel. All right, so here's my plot here. And I just selected a handful of the data in our overall data set here. All right, so if you guys are following along, the things that I've already done to this data set that we did last time, I removed all the -999s, or -9s, sorry, that for missing data. And then I got rid of some blank rows that just make it easier for me to plot things and select groups. So other things I'm going to come in here, I'll get rid of this plot. I don't really need that. I'm going to get rid of this bromine column, get rid of our criteria columns, get rid of all this stuff over here that I don't really care about, just keep it to our chemical variables and the year and the site IDs. All right, so let's say that our question here is, like I said, whether or not there is a statistically significant relationship between nitrate and ammonium concentrations in this data set. So Excel has some ways that we could do this. I showed you last time we can calculate the r² using this equals RSQ formula. But that only gives us the r². And like I said, that's not a statistical test. It gives us some idea whether or not these two variables move together in the data set, but it doesn't tell us whether that's a statistically significant relationship. So what I'm going to ask you guys to do, if you're following along here, is go to the File tab. We're going to go down to Options at the bottom here. And we're going to turn on a couple of add-ins that come with most distributions of Excel. If you guys don't have these, let me know, but you should have access to these couple ones that come with Excel. So we go to add-ins, click on it. And you can see up at the top here, I've already got some that I've activated. So I've got this Adobe PDF Maker, and then I've got this Analysis Tool Pack and Analysis Tool Pack VBA. Those are the ones you guys are going to want to add in. And to do that, down here where it says Manage Excel Add-ins, just click on Go. And it should bring up this window here. And you should be able to click on Analysis Tool Pack and Analysis Tool Pack VBA. And then when you're finished, click OK. And now there should be something new in Excel for you. If you go to your Data tab, all the way over on the right is this Data Analysis button. And that's what we're going to use to do our linear regressions here. So if I'm on my tab with the entire data set here, I'm going to come up to the data analysis button and click on that. And now it gives me all these cool statistical tests that we can use. Some different kinds of plots we can make. There's a bunch in here that you can explore. And if you want to learn more about this, if you click on this help button here, it'll take you to this Microsoft help page that explains all of these different options that you have. It gives you some information on how to interpret the outputs as well. All right, so the test that I want to do here is a regression. So if I click on regression and click OK, it's going to ask me for an input Y range. So our Y range is our dependent variable. And in the example that I gave you, that was nitrate. So I'm going to come over here. I'm going to select the first 25 cells in nitrate. Let's see, go down to 25. Because that's what I plotted on the figure there. So I'm going to try and keep it consistent with that. Then for the X range, our dependent variable here is ammonium. Select first 25 cells in ammonium as well. And now I've got some options down here. If I've selected the labels up at the top, I have to make sure this labels box is clicked. Otherwise, it won't give me a value. It'll tell me I have a text error. This confidence level right here, the one that we typically use in science is 95%, which means we've got a 5% chance of getting a spurious false positive, saying that there is a relationship here when there really isn't. And that's just a general guideline that is used throughout science as an acceptable amount of error. That doesn't mean that you can't change that value for certain reasons, but for right now, we're going to be using a confidence level of 95% or a 5% error rate. And then down here, we can have it plot a couple of different things. I'm just going to have it plot these line fit plots because we don't really have time to get into how to interpret all of these other plots that it can make. And I want it to output this in a new worksheet. And if I click OK, now it has made a new worksheet here, sheet 17. And it's given me a whole bunch of output data over here and made this plot. This plot looks similar to, what I made in the PowerPoint. So same data points. Instead of putting a line of best fit, it plots these what it calls predicted nitrate values. So it's using the line of best fit that's shown in the PowerPoint to calculate these values based on the given ammonium values. But how do we decide whether or not this relationship is statistically significant? So if we go over to our output over here, it gives us some general statistics about the regression. So it gives us a bunch of different measures of how well the data fit, or how well the line of best fit fits the data. So we've got this R value, we've got R squared, we've got this adjusted R squared, which is adjusting for the number of observations. And if we look at this R squared here, it should be similar to the one that I've got in the PowerPoint, unless I selected a different number of data points. But what we're really interested in is down here. So in this, this block that's labeled ANOVA. And the values that we're interested in here is this F statistic, and then this significance of F. So what the significance of F is telling us is this is a number that we can compare to our acceptable error value of 5%. So we want to compare this number to 0.05. Or if we were to turn that into a percent, it would be 5%, but we do everything in proportions instead of percentages. So the question here is this number, the significance of F, less than our acceptable type 1 error rate, is 0.05. And this is 0.000028. So it's certainly less than 0.05. So what this tells us is that we do have a statistically significant relationship here between these two variables. All right, there's a whole bunch of other values down here. You'll notice if you've taken statistics, you know, one of the things that we always look for is a result from a statistical test is a p-value. And these p-values are given in this column here. And what this tells us is that our intercept for the curve for the line of best fit, which is, you know, right around 0.25, our y-intercept, is statistically significantly different from 0. And then our slope here is statistically significant with respect to our independent variable, or sorry, with our independent variable of ammonium. So, and you'll notice this number is exactly the same as this. So the significance of F is our p-value for the slope to tell us whether or not these two variables are significantly correlated. All right, so that's what you would do to look for a statistically significant relationship between two variables. If you've got a lot of variables and you just want to do kind of like an exploratory thing and you don't want to do this individually for each one, you might create a correlation matrix. So if I go back here and I just want to know like which ones of these variables are related to one another, and I don't want to go through and weed through this by hand or run individual regressions for each one, another option that we've got in the data analysis tool pack is correlation. Click on correlation. And now I'm just going to grab all of our chemical data here. So I'm going to take calcium, magnesium, all of our ions. I'm going to get pH. We'll get conductivity in there as well. And I'm going to select all the data points in our entire data set. And click OK. And now what it gives me is this matrix of R² values. So the way that we read this is we look across one row and read the column where they intersect here. And this tells us the R² for the correlation between calcium and calcium, which should be an R² of 1, right? If we plotted the calcium concentration versus the calcium concentration, it should be a straight line. So all of these values along the diagonal here are 1 because we're comparing the same variable to itself. Now these other R² here are giving us the relationship between different variables. So we want to see which variable is most closely related to calcium. Look down here and try and find which one of these has the highest overall value. And in just scanning through here, I see 0.48 for ammonium. So it looks to me like calcium and ammonium have the strongest relationship out of any of these variables relative to calcium. Another way we can kind of visualize the data here is, I'm just going to get rid of these ones because it's going to make what I'm doing next look a little weird. But we can use that conditional formatting option and set a color scale. So let's say we want our high values to be green and our low values to be red. Now this makes it a little bit easier for me to visualize which relationships are important. I see right here that sodium and chloride have an R squared of 0.98 overall for the entire data set. So that's really high, which tells me that they're probably coming from the same source in the environment, which is the truth from what we know. But I also see important relationships between magnesium and sodium, magnesium and chloride, sulfate and nitrate, conductivity and nitrate and sulfate. And then I see these negative values here too. So what this tells me is that there is like an inverse relationship between, let's say, sulfate and pH. So the higher the sulfate, the lower the pH. And we showed that last time when we walked through what we were doing in the last class. So the values that are the most negative, closest to -1, and the values that are closest to +1 show us the most important relationships here. And then we might want to go through and test these guys using linear regression to see whether these are statistically significant relationships. With an R squared of 0.98, you can almost be assured of that, but you still want to do the statistics. Okay, so that's correlation, looking at correlation coefficients, as well as running a linear regression. Questions on that? Okay. So for those of you in your papers who are kind of like interested between the relationship or interested in the relationship between two variables, this might be a statistical test that you could do very easily for your poster presentation. If you have if we can find the right data set for you to use. Okay, let's say we're interested in whether or not two variables or two samples of the same variable are different. So if we look over on the right here, we've got two examples of a distribution for different samples. So up in panel A, we've got the red sample, which basically, let's say this is tree height. We're going out and we're measuring the height of trees in College Woods. And we go out one day and all the trees we measure some that are shorter, we measure some that are taller, and they have this mean right in the middle of this distribution here of mean 1. Then we go back out, let's say a year later, we measure the same trees again, and we want to know, have they grown? All right, our mean has increased, but has it increased a statistically significant amount? And the question here is whether or not there's enough separation between the means or whether we've got too much overlap in these distributions, so it's not really a statistically significant difference. Maybe we just went out and we measured differently the second time. You know, we had a different ruler, or whoever was doing the measurements didn't know how to read a number line. So the question we're asking here is whether or not the mean of our two samples is different. So we can go back and do an example of this in our data set. And there's a couple different ways we can do this. One of the things I want to show you first is how we can calculate the summary statistics for all of our variables all at once. You know, last time I showed you how to do it individually using these built-in formulas like average and standard deviation, and things like that. There is a shortcut in the analysis tool pack to do this as well. I still like to do it by hand just because I can calculate the values that I want, and the analysis tool pack only gives me what it's pre-programmed to do. But I'll show you how that works so you have it in your toolkit. So go to the data tab, go to data analysis, and we're going to calculate our, where is it, descriptive statistics. Click OK. And I just want to get descriptive statistics, let's say, on just all of our ions for the entire data set. And I want to calculate our summary statistics, and I want to put it in a new worksheet again. Okay, so now it spits out this new worksheet. We got a table here of all of our ions along the top. And for each one, it has calculated the mean, standard error, median, mode, standard deviation, variance, kurtosis, skewness, range, min and max, the sum, and the total number of data points. All right, so this is an easy way to do that. The only issue with this is, these are just numbers in here. They're not formulas. So if you wanted to go back and change the range of cells that you're looking at, you got to go back and actually, rerun the calculations again. You can't change them right here. And it doesn't have the ability, to add in things like percentiles if you want the 95th and 5th percentile of your data set or something like that. You got to go back and calculate that individually. But in the assignment, I'm going to ask you to calculate summary statistics. You can do it this way. You can do it the way that we talked about last week as well. All right. So one of the things it does is it calculates the mean here. So we've got a mean of 0.17 for calcium, 0.03 for magnesium, 0.03 for potassium. What if I wanted to know whether or not the mean of concentration of calcium and, let's say, sodium was different? Right here, calcium is 0.176, sodium is 0.160. They're pretty close. I mean, calcium's higher, but is it statistically significantly higher? Let's find out. So come back to our data set, and now we want to run a t-test. And our question here is the concentration of calcium different from the concentration of sodium in our data set? So what we want to run under data analysis is a t-test. And there's a number of different options here. And unfortunately, we don't have time to get into too much detail about this. But the ones I'm going to show you are assuming equal variances and assuming unequal variances. So if we look back at our summary stats, it calculates a sample variance for us in this row here. And for calcium, it's 0.03. For sodium, it's 0.08. So are those equal variances? Statistically, we'd have to do some testing to figure that out. But I'll show you the difference between calculating it, assuming that these two variances are equal, and assuming that they're unequal. So the data analysis, we're going to go back and choose t-test with assuming equal variances. All right, and for variable 1, we're going to do all of our calcium values. For variable 2, we're going to do all of our sodium values. And I did select the top row, so I got to click this labels box. And we don't have a hypothesized mean difference here. That's not part of our hypothesis. Our hypothesis is just that the means are equal. That's our null hypothesis. And our alpha value here again is that 0.05. That's our acceptable type 1 error rate value. And if I click OK, it gives me this output here. So come on, show the whole thing. There we go. All right, so what we've got up here is it calculates a couple of the summary statistics that we're interested in, our summary values for calcium and sodium. So it calculates the mean, the variance, and the number of observations. Calculates the overall variance for both variables here. Our hypothesized mean difference is 0. We're saying they're the same. That's our null hypothesis. And then it calculates this t-stat value and then a couple of p-values here. So this p, this is the probability that our t-statistic from a known distribution is less than or equal to our calculated t-statistic. And there's a couple different things here. So we've got this one tail and two tail. So one tail is if we assume, like in our example, that trees can only grow up, and we know that the difference can only go one way, then we would use a one-tailed test here. But let's assume that trees can grow up, or they could, I don't know, lose their top branches and become smaller. So then we would use a two-tailed test. In this case, we don't know whether sodium or calcium is going to be higher. We have no pre-existing data to tell us one thing or the other. So we would go with the two-tailed test here as well. All right, and our p-value for this is 1.1 times 10 to the minus fifth, which is certainly less than 0.05. So this is a statistically significant difference in the means. So we can say that the concentration of calcium in this data set overall, the mean concentration of calcium is greater than the mean concentration of sodium. And we can say that with some 95% confidence here. All right, if we do this assuming unequal variances really quick, so we'll just come back, run the same thing again, except we're going to use this t-test 2 sample assuming unequal variances. And we'll do calcium versus sodium again. And put it in a new worksheet. Okay, we get a similar output. And in this case, we get effectively the same p-value for this test, the two-tailed p-value. Right, it was 1.1 e to the minus 5, and this one, it's 1.1 e to the minus 5 in the unequal variances. So the difference in the variance here between these two samples has no impact on the calculated statistical significance, meaning they're close enough to meet the assumptions of the t-test. So that's how we would look for the difference between two samples. So another example we could do with this data set would be, let's say instead of looking at the difference between two variables, let's look at the same variable at two different sampling sites. So let's take this let's just pick 2 sites here. I'm going to pick, let's just pick these first 2 Alaska sites, AKO1 and AKO2. All right, and now I want to, let's say I want to know whether or not the sulfate concentration is different at these 2 sites. So my null hypothesis is that there's no difference in sulfate between AKO1 and AKO2, but I'm going to run a t-test to figure out if that is true. And I'll just do the unequal variances one here because one of the other things we got to watch out for here is whether or not they have the same number of data points. And if they don't have the same number of data points, it's often recommended to just use the unequal variances option. All right, so I'm going to take sulfate for AKO1 as my first variable, and then sulfate for AKO2 for my second variable. And you can see we have far fewer observations for AKO2 than we do for AKO1. I don't have labels in there. And okay. All right, so now we can see our calculated means here, 0.17 for AKO1, 0.18 for AKO2. But if we look down at our p-values here, our two-tailed p-value, we got a value of 0.45, which is greater than 0.05, which means not or no statistical difference. All right, so any questions on doing the summary statistics or t-testing? There's another way to run t-tests in Excel. I'll show you really quickly here. You don't actually need to use the data analysis tool pack. We could just do equals t.test as a built-in formula. And it wants our first variable, so I'm going to select calcium. Our second variable, I'll do sodium again. The number of tails, so we want a two-tailed distribution, so we type 2. And then it asks us whether we want to do a paired test, 2-sample equal variance or 2-sample unequal variance. I'm just going to pick the unequal variance one for now. If I hit enter, it gives me a p-value. So my p-value here is less than 0.05. So this tells me again that the concentration of calcium is different from the concentration of sodium. So a couple different ways to do a t-test there. All right, if you have any questions, just type them in the chat or jump in here. Ask as I go along. Okay, the last thing I'm going to go over in terms of data analysis in Excel is what if we've got more than 2 samples? What do we do? So let's say we were interested in whether or not there's a difference at any of the sites in Alaska in the, let's say, sulfate concentration. What we're going to do is what's called an analysis of variance, or an ANOVA. And the way that this works is, if you look at the image over on the right here, we've got a yellow sample. Let's say that's site 1, blue sample, site 2, red sample, site 3. Each one of these samples has its own mean and has its own variance. And some of the distributions overlap and some of them don't overlap. And the question that we're asking in ANOVA is, are any of these sample groups, does it have a mean that is statistically different from the overall mean for all of the sites or all of the groups? So in this image over here, it's asking, is mean number 1 different, statistically different from grand mean? What about mean number 2? And what about mean number 3? And then I'll show you, this is going to give us one p-value that tells us either there are differences or there are no differences. And then we would follow that up with individual t-tests to see which groups are different. So going back to Excel here, we want to run an ANOVA, and I am going to pick, so we have 2 Alaska sites here. I'm going to grab 2 more. So I'll get AK03 and AK06. And now I'm going to conduct an ANOVA on these guys to determine whether or not there is any statistical difference amongst these groups. And I have rearranged the data on another tab down here. Where did it go? I believe. Okay, yeah, here. All right, so I'm going to get rid of this guy. All right, so what I've done is I've come and I've taken the sulfate values for AK01, 2, 3, and 6, and I've parsed them out into their own columns here. And now the question I'm asking is the sulfate concentration at any one of these groups different? Let me hide this right now. So I've calculated the mean sulfate up here, and we've got 0.18, 0.19, 0.27 at O3, and then 0.18. So O3 looks like the one that is kind of like the Sesame Street, which one of these things is not like the other. Let's find out if it is statistically significantly different. So go into data analysis, and we're going to go select ANOVA. And we've only got a single factor that we're considering here. That is, we're only considering a difference in the sample location. If we wanted to consider a difference in the sample location and then also like the sample year, then we would have we would run a 2-factor ANOVA. But we're going to run a single factor. And I'm going to select just this range. And again, I've got my labels in the first row. My data is grouped by columns, so I've separated out the sample sites into their own columns. I could do this in rows as well. And then my alpha level is 0.05 again. And I'm going to output this into a new worksheet. Okay, now our output for the ANOVA here. Again, up at the top, it gives us some sort of summary of the data. It tells us how many samples we have in each group, the sum of the values, the average, and the variance. And so actually, this looks like a different number here. I'm not sure what's going on with that, but I would have to go back and look at it in more detail. So looking at the averages here, they're all pretty close to one another. And if we look down at the results of our ANOVA, it gives us a bunch of statistical values here that are important, but we don't have really time to get into these. But what we're really interested in looking at is, again, the F statistic and then the p-value. So here we're comparing the F statistic to this F critical value, and we want our calculated F statistic to be greater than this critical value. In this case, 0.16 is not greater than 2.7. And so we end up with a p-value that is not, not what I meant to hit. A p-value here that is not statistic or indicates that there are no statistically significant differences between these four groups. All right, so if I go back here and not that one. If I go back here and let me just let me grab another year or another site from Alaska. So I'm going to grab, apologies, sorry. I'm going to grab AK97 as well. So come over and get its sulfate values. And then we'll go back here. I'm going to put AK97 into the mix now. You can see its mean value is 0.368. Ah, I see what's happening. There we go. All right, so now if we rerun this ANOVA and we consider all of these sites, let's see if there is a difference between any of these sites now that we are including AK97. Okay, again, we've got our calculated summary stats up here, average and variance. But now if we look down here at this p-value, it's 2e⁻⁷. And you can see our F statistic is far greater than the critical F value. But really what we're looking for is this p-value. Is it less than 0.05? Yes, it is. And what this tells us is that there is some statistical difference amongst these five groups. In order to figure out which ones are statistically different, then we have to come back in and compare each group to one another using a t-test. So I've done that in here using the method that I showed you. And what we call these t-tests that we do after an ANOVA, call these post hoc tests. So it's after we've determined that there's an initial difference between the groups, we come back in and try and look for differences between individual groups. So what I've done here is calculate the p-value for site 1 versus site 2, site 1 versus site 3, 1 versus 6, and then I gotta fix this one because I deleted 97 before. That. And 1 versus 97. So, and then I went through and did this for all the other comparisons we could have. Group 2 versus, or site 2 versus site 3, 2 versus 6, 2 versus 97. 3 versus 6, 3 versus 97. And then 6 versus 97. This one. And then I used some conditional formatting here to highlight any values that were less than 0.05. We can see any comparison to site number 97 has a statistically significant p-value for that t-test. So the oddball amongst these five groups is definitely AK97. it has a much higher mean sulfate value. And that might be something that we want to go back in and try and figure out why that is from some additional testing or understanding the data better. And I guess that is about all we're going to be able to get through today. Next time I will introduce the assignment that I'm going to ask you to do for this. It is not going to be overly time consuming, but I am going to ask you to do some of the same manipulations that we've done over the past 3 lab or sessions, meetings, whatever you call them. Okay, so questions on this, questions on paper, anything going forward?
You said you were recording this this lecture. Will you
I-
just post it on As You Learn?
Yeah, and I'm trying to maybe utilize YouTube as well, so I can add timestamps easily.
Mm-hmm.
So you guys don't have to like go through and find the right point. I can just timestamp when I'm talking about t-test versus correlation. But that might take me a little while to get up there, but I will post this right after class.
Okay.
Speaking of that, let me stop the recording.